Hello, how's it going? In this video, we'll be evaluating this following integral. So the integral from negative infinity to infinity of cos x over x squared plus 1 dx. Okay, so this integral we'll be solving using complex analysis. So, yep, it'll be pretty similar to the other videos that we have done on this channel. So how do we actually do this using complex analysis? So what we do with complex analysis is we basically take the function that we're integrating and put it in terms of f of z, so a complex variable z. But we basically replace the x's with z's, and we replace any trigonometric terms with Euler's formula e to the I x. But in this case, it'll be e to the I z because we're going to be putting it in terms of z. So this is what we do to start off. Okay. We go, alright, let f of z equal to e to the I z, so this replaces our cos of x, divided by z squared plus 1. Okay? Now we basically got to find if there's any poles. So a pole is basically points where this function has like singularities where it's like, for example, since this is a complex function, if we have z is equal to I or negative I, this whole thing will be equal to, the bottom bit will be 0, because if you have I squared on the bottom, you get negative 1. If you have negative I squared, you're going to get also, you'll get another pole there. So what we can actually do is, knowing this, is actually we can factorize the numerator of this. So we can use basically just a difference of squares. So we can just say, alright, z squared plus 1 is the same as z plus I multiplied by z minus I, okay? So the way I went from there to there is basically because, alright, the square of I is negative 1. So this expression here, z squared, is equal to minus I squared, okay? So you can see how those are interchangeable. And all I did was a difference of squares of this, and that's how I got to there. Alright, so this tells us where the poles are at. So we have a pole. Oh, that's how you spell pole. We have poles when z is equal to negative I and z is equal to I, okay? So now all we're going to do is integrate over a contour. So a contour is basically going to have an Argand diagram, and you're going to integrate over some like pretty much a contour. So we're going to integrate, we'll just use a semicircle for now. So we'll go from R to negative R, then we'll go around here, and there's no singularities on the real axis, so this is our real axis and this is our imaginary axis, and it goes from here. We're going around like this. Okay. We have our pole I is going to be up here, and we also going to have one down here. We only have one in our contour, and this is a path gamma, so this is a particular path here going around. So we only have one pole in here. So if we're integrating over a contour, this is going to be basically equal to the residue theorem. Okay. But we can basically break this contour integral up into its parts. So what we do is basically say, alright, our contour, so that's why we put a little circle in the inside an integral to represent a contour integral, because it's a closed region. That's why we have a circle. So integral over a path C, so this is our contour C, is this path around here of f of z dz is equal to, we can basically say it's the sum of the parts. So it's the integral from over the path gamma, and of course that's going to be in the imaginary complex plane. So we're going to have f of z there. So it goes around path gamma, and it goes then from negative r to r. But notice when we go from negative r to r, we're on the real axis. So we can put it in terms of f of x. So we'll go from negative r to r, and we can have f of x because it's all real numbers on the real axis, okay? And this whole thing is equal to the residue theorem because we have a pole inside our contour. So the residue theorem is basically our contour is equal to 2 pi I multiplied by the sum of the residues of f of z, okay? Now f of z, let's find the residue. So we only have one z equals I. So the residue is basically when z is equal to I of f of z is basically equal to the limit as z approaches I over, if we rearrange this, we'll have z minus I here. So we'll have z minus I multiplied by f of z, which is e to the I z over z plus I over z minus I. that cancels. As this limit approaches, we're going to have e to the I squared at the top, and we're going to have 2i on the bottom. So simplifying that, that goes to 1 over 2ie, I think. Yep. So then we place this up here. So we're going to have 2 pi I multiplied by 1 over 2ie. The 2i here cancels there. So we're left with pi over e. Now this is actually the value of our integral up here, but we can't really prove that yet. So this is what we're going to do. So our contour integral over the path c of f of z is equal to the path over gamma f of z, which is e to the I z over z squared plus 1 dz, plus the integral over the real from negative r to r over the real axis, which is going to be e to the I x over x squared plus 1 dx is equal to pi over e. Now, we can basically almost turn this integral here into the one that we're trying to integrate, but we got to change the bounds. We've got to basically make r go to infinity to get our bounds right. So we apply a limit to everything. So the limit is r goes to infinity over this integral here, so over the path gamma, e to the I z over z squared plus 1 dz, plus the limit. As we apply this limit to here, these bounds are just going to change. So I'm just going to change the bounds and not put a limit there. So I have negative infinity to infinity e to the ix over x squared plus 1 dx. We can't apply a limit to a constant because there's no variable r there, so we'll just leave it as pi over e. Now, we have to evaluate this. What is this going to turn into? So, this is what we do. Basically rewrite it. So we've got to prove we've got to basically show what this goes to. So let's just make a little substitution. Let z equal to, let's say, r e I theta. Okay. So we can make this substitution because it's basically going to be, it's basically equivalent because it's like terms of a rotation. So if we're replacing z with r e to the I theta, that logically makes sense because the radius of this semicircle here is r. That's that point there. And this e to the I theta is the x and y components. So it's a valid substitution you're making there. Okay. So, but notice since we're doing a semicircle, theta is only between 0 and pi radians, okay? Because we're only looking at a semicircle like this. So it's going from 0 radians to pi radians, etc. Okay? So, before we make the substitution, we need to find out what dz is. So dz, differentiating both sides, we're going to have r I e to the I theta. Now we can make the substitution. So, integral over gamma of e to the I z over z squared plus 1 dz. That turns into, we'll just replace the path gamma with 0 and pi because we're doing it in terms of theta now. So 0 to pi over e to the I multiply, oh, this is going to be yucky looking, e to the power of I multiplied by r e to the I theta. So I r e to the I theta. That's very yucky. And then we're going to have the bottom bit, we're going to have r squared to the power of 2I theta plus 1 multiplied by r e to the I theta d theta. I forgot the d theta here. Okay. Now, is there anything that can cancel? Nope. But we can take basically this I out the front door, and we can also, what can we take out? We can basically take the r and I out the front straight away. So we can have this integral, so r I of the integral of 0 to pi and e to the I r e to the I theta. And then you have, what do we have left? E to the I theta here. These are multiplying over r squared e to the 2I theta plus 1 d theta. Okay. Now, if we were to apply the limit straight away, what would we get? So if we had r go to infinity, we still it won't give us a logical value here because we have an r squared here, an r there, and an r at the front door. So it's not really going to change anything at all, okay? So we can't apply the limit just yet. So what we can actually do is basically say, all right, this integral is equal to, let's just say I, okay? Now there's an inequality. Now, if you take a direct path is always shorter than the detour. So that means if you have the absolute value of this integral, it's going to be less than, how is it, less than or equal to, let me just think about it for a sec. If it's less than or equal to, then you're going to have like, hold on, I just need to check my notes for a sec. Yeah, that's correct. So if it's less than or equal to, you're going to have basically, it's going to be equal to the modulus of IR over the integral of 0 to pi, the modulus on the inside, e to the IR, e to the I theta, multiplied by e to the I theta, divided by r squared e to the 2I theta plus 1 theta, absolute value, d theta. Now, so this integral up here, I absolute values, that's basically taking this whole integral and putting absolute values of this. Now this integral here is less than or equal to if you did the absolute values of the individual parts pretty much, okay? Now, how does this actually help us? Now we can actually we can basically break this up, so we can put the absolute values on just the top and bottom, we can do that. And we can change the front, so the absolute value of IR is just going to be R, because the modulus of I is just, it's only one unit in the imaginary plane, so it's just 1. So this leaves us with modulus of I is less than or equal to R of the integral from 0 to pi of the modulus of e to the IR I theta multiplied by e to the I theta over r squared e to the 2I theta plus 1. Okay. Now, the reason I wanted to do this is because we can basically use the reverse triangle inequality now. So recall, if you have the modulus of a minus b, that is less than or equal to the modulus of a minus the modulus of b, or modulus, okay? So this is the reverse triangle inequality, and it's been proven in several books and stuff. Hold up, let me just think for a sec. No, that's incorrect. It's the other way around. I'm pretty sure it's the other way around. Let me just, I'll just double check. I wrote it down before as well. Yep. Yeah, that's all good. Alright, cool. So the reason we can do this is basically we can have this part here and put it into this inequality. So if we just change and fudge it down here, we can have, instead of having a plus sign, we can have minus multiplied by -1, and that's still the same thing. So therefore we can put it into this inequality. So you have r squared e to the I theta minus -1, which is a bit of a cheat, is greater than or equal to the modulus of r squared e to the I theta modulus minus -1. So we're left with, alright, modulus of this is just going to be r squared. So we'll have r squared minus 1. Now r is strictly positive, so we can get rid of these absolute value signs now. So this whole thing is less than or equal to this pretty much, r squared e to the 2I theta minus -1. Now the beauty about this is if we take the reciprocal, because we're looking at the reciprocal in this integral here, if we take the reciprocal, we can actually flip the sign of the inequality. So e squared theta minus -1. Okay. You're going to have 1 over r squared minus 1. Okay. Now how does that help us? Basically we can set up another integral. We have like a triple inequality. So we have the modulus of I is less than or equal to r integral of 0 to pi. Actually, I'm going to make this a bit smaller because it's going to get in the way. So just move this up here for a bit. Okay. So we'll have all this. R squared to the I theta minus 1 d theta. Now this whole thing is less than or equal to the integral now of r over the same bounds, the numerator is still the same. So we'll have e to the I r e to the I theta multiplied by e to the I theta modulus over this new thing here. So I have r squared minus 1 d theta. Okay, now here's a trick we can do now. We can just take out the r squared minus 1 out the front door because it's not dependent of theta, okay? It doesn't rely on it. So we actually just have basically this down here. So we'll have the modulus of our integral. Oh, see, there's what I do. No, modulus of our normal integral is less than or equal to r over r squared minus 1 over our integral from 0 to infinity of pretty much this here. Okay? Now, we don't have to go any further. We could, but we don't have to. If we apply our limit as r goes to infinity, this whole thing here is going to go to 0. While this up here is going to go to infinity, down here we're going to have 1 over infinity. And now this 1 over infinity, since it's r squared and this is just r, this 1 over infinity is going to go to infinity faster than this r is going to go to infinity just because of the degree of power. So therefore this whole front term is going to go to 0 as r goes to infinity. So as r goes to infinity, this whole thing here goes to 0. So if our modulus of our integral is less than or equal to 0, in order for that to be true, it has to be equal to 0. So therefore our gamma integral all the way up here as r goes to infinity is 0. Alright, so we're left with this now. Now we want the integral of cos x over x squared plus 1, don't we? Now recall Euler's formula. E to the ix is the same as equal to cos x plus I sine x. Okay? So we can break this integral up into its two parts. So we have the integral from negative infinity. So we'll have cos first, so we'll have cos x over x squared plus 1 dx plus the integral from negative infinity to infinity I sine of x over x squared plus 1 dx is equal to pi over e. Now you notice this answer here is strictly real, so and this integral here has imaginary parts, so this integral is invalid, therefore this integral here is equal to pi over e. So we'll just write it now at the top to make it all fancy. This whole integral evaluates to pi over e. Alright, thank you so much for watching. I hope you enjoyed this video and you learned something. If you have any questions, leave some in the comments and I'll try my best to answer them. See ya.